I'm going to present this paper. The title is RapidChain, Sharding-based protocol, and this paper was published in CCS. By default, the sharding-based protocol has two issues. The first is scalability, and the second is security. Because one large network is divided into several independent small networks, the scalability improves while the security becomes less. So the RapidChain is Byzantine resilient public blockchain protocol, and several small groups are called committees, and committees process transactions in parallel and maintain independent ledgers. So by performing consensus and storage in parallel, sharding-based protocol can achieve throughput proportional to the number of committees. And this is an overview of RapidChain. So how peers discover each other in the network and how they are verified for transactions across committees. So how to agree within the committee and how to reconfigure the protocol. So I will briefly explain peer discovery and inter-committee routing. Each committee maintains a disjoint transaction ledger, and if a committee sends a transaction, then the transaction is stored in a specific committee where it must be stored. So the committee at the time is called an out committee, cout, and in other words, every committee is an output committee, and each committee stores a different specific transaction. Before a block is appended, all committees must verify that the transaction is valid. Then RapidChain uses the UTXO model, and this UTXO model, multiple inputs can be stored in different committees. So the output committee needs to communicate with committees that have inputs. At this time, the committee having this input is called the input committee. And then this is the intra-committee consensus. The leader of the output committee creates a block and send it to all members. All members of the output committee go through the process of agreeing on the same block. And after a certain amount of time, the protocol needs to reconfigure. Committee members are reconfigured because members of the committee may come out and new nodes may come in. Prior to describing the outline I just mentioned, RapidChain requires a bootstrap process. This bootstrap will only run once at the start of the RapidChain and will configure the necessary committees. Suppose we have 1-3 of the corrupt nodes in the network, and then initially all nodes are configured as bipartite graphs. And this bipartite graph is called sample graph. In this graph, L represents network nodes and R represents groups. That is, all nodes are placed into multiple groups. So in this figure, level 0 represents all nodes and level 1 represents groups. So that is, level 0 and level 1 represents bipartite graph. When groups are created using the sample graph, they perform an election procedure. They create subgroups from groups and repeat this process, which ultimately constitutes just only one root group. So to create a subgroup, the members of each group create a random string, and it notifies the random value and its ID. If it has been elected by hashing it, and all nodes sign and gossip the IDs of the elected nodes with the smallest h. And the elected nodes gossip this information and prove to let them know that they have been elected. If more than e nodes from the group correctly announce they got elected, then the group is dishonest. By grouping and subgrouping iteratively, that is by chaining several graphs, one final root group is constructed. Most of the members of this root group consist of honest nodes, which is due to probability. And this root group creates a first committee called the reference committee, and the fraction of corrupt nodes in the generated committee is bounded to 1/2 with a high probability. This is demonstrated by the hypergeometric distribution and will be explained in the next slide. And the reference committee is responsible for performing periodic reconfiguring between epochs, and then the reference committee also randomly organizes all the nodes into committees. Use the hypergeometric distribution to calculate the failure probability for the committee formation, and notation is as follows. The entire node is n, the nodes in one committee are m, the n-most corrupt nodes is t, and the number of corrupt nodes is x. The failure probability for just one committee is follows. So we select m out of n and choose x out of t, and choose n minus x out of honest nodes. So we add this all probability until x is m, then we can get the failure probability for just one committee. This figure shows the failure probability according to committee size. It shows the probability of failing to create just one committee of 2000 nodes. So as the committee size grows, then the probability failure decreases. So once committees are created, then the peers use Kademlia routing algorithm to communicate with each other. So Kademlia is an XOR distance-based algorithm. For example, there are A, B, and C nodes. The ID of A is 1111, and the ID of B is 0111, and the ID of C is 1110. So the XOR operation of A and B is 1, 0, 0, 0, and the XOR operation of A and C is 0, 0, 0, 1. So at this point, the distance between A and C is considered to be closer than the distance between A and B. And this is the example. There are 8 nodes. This is the 8 nodes. And a node R with an ID of 14 is 10 away from a node with an ID of 4. The node closest to the half of the distance of R among the nodes that nodes is contacted. So node R then contacts node 0, which repeats until node ID 4 is founded. XOR distance enables node discovery in log n steps. So apply the Kademli algorithm in RapidChain. When a user sends a transaction, it is sent to the arbitrary node and eventually sent to the output committee. So in this figure, committee C0 wants to find C7 through C4 and C6. Input UTXOs can be associated with multiple committees in cross-shard transactions. So here the transaction ID is 9, and when the user sends a transaction, input transaction is transaction 5 and transaction 8. So the newly created output through this transaction is row 1 and row 2 of transaction. So if the node receives this transaction, then checks whether the input is not used to verify that the transaction is valid and whether the sum of the output is less than the sum of the input. Before knowing how to deal with cross-shard transaction in RapidChain, let's first look at how OmniLedger handles it. OmniLedger is also a sharding-based protocol. Another sharding-based protocol, and OmniLedger proposed Byzantine shard atomic commit protocol, which is called atomics, and where each transaction is committed or eventually aborted. So this purpose of this protocol is to ensure consistency of transactions between shards and to avoid double spending and to prevent unspent funds from being locked forever. So this atomics protocol consists of 3 steps. First one is initialize and lock and unlock phase. So I'm gonna explain the initialize step first. In this step, input shard and output shard are present at this stage, and the client creates a transaction called cross-shard transaction, which includes input and output. Input consumes the UTXO of the input shard, and output produces the new UTXO from the output shard. The client got this transaction. And this is the lock phase. If the transaction is valid on the input shard, the leader of input shard marks in the state that the input was used. And Kashif's proof of acceptance, which is the Merkle proof of the block containing the transaction. So at this point, the transaction is blocked. If all the input shard leaders issues proof of acceptance, then the client generates an unlocked commit transaction, unlocked commit transaction. And this unlocked commit transaction consists of a locked transaction and the proof of acceptance for each input UTXO. So the output shard verifies the transaction and includes it in the block. So this updates the state and enables the expenditure new funds. And this is the unlock to abort phase. So if even one input shard issues a proof of rejection, then the transaction cannot be committed and must be aborted. So eventually the client requests unlock for the associated input shard. When the input shard receives the request, then the reader rewrites the original UTXO to be consumable. So this is the entire atomic protocol. If the client creates a cross-shard transaction and its transaction input is valid, and it will receive proof of acceptance and commit. So, however, if it is not valid, then the client requests an abort. But RapidChain pointed out this drawback of this omni-ledger. First, one proof must be created when the transaction is cached. This causes large communication overhead, and then the second is to give the lightweight user node an extra burden. Thus, in RapidChain, the user does not attach any proof to the transaction. When a user sends a transaction, we have two inputs and one out. Assume we have two inputs and one output, and then the leader of the output committee creates three transactions. The input and output amounts of transaction 1 and transaction 2 are the same, and each output is used as the input of transaction 3. So the leader sends each transaction 1, 2 to the input committee. If the input UTXO is valid, then the input committee sends the output to the output committee. If both inputs are invalid, the two input committees do not send input, and so eventually transaction 3 is not accepted. Instead, just only one input is valid. Then while the remaining input is invalid, transaction 3 is not accepted, but valid UTXO is available to the user. So to increase the efficiency of cross-shard transactions, send a batch of transactions. So output committees combine and transmit UTXOs belong to the same input committee, and the input committee verifies each UTXO. After the committee is created, it runs the protocol for a fixed time called epoch, and this epoch includes multiple iterations. For each iteration, the committee picks the leader, and this leader creates a block and then cache block and block header, including iteration number. So the next 4 rounds will be an agreement, leader gossips message containing headers and header and tags, and all nodes echo their headers. If the leader gossips more than one version, then the honest node will reject and pen the tag. If the honest nodes receive the same echo more than a majority, they will send the tag accept. And then committee configuration is handled by the reference committee. So to prevent severe attack, the reference committee checks the POW solution for all nodes and let all the nodes solve the POW offline so that the protocol is not stopped. So I will explain the committee reconfiguration by epoch I-1 and I plus 1. Epoch in step I-1, the reference committee generates a random string, and epoch at the end of step I-1, we expose a random value to prevent all nodes from pre-computing. So now epoch I step T, all committees receive a random value, and the nodes that want to participate in the next epoch proceed to find the solution. So they have to find X value. So the reference committee receives and confirms the solution of the node to join before the end of epoch I. If the solution is accepted, the reference committee adds that node to the list of active nodes. So the active nodes list is a list of nodes that will participate in the next epoch. And then at the start of epoch I plus 1, they exchange committee members. So the reference committee divides committees in half. One group is called an active committee set, with the active members being more groups, and the remaining groups are called the inactive committee set, with the active member less than the active committee set. The reference committee randomly selects one committee from the active committee set and adds the new nodes to the committee. Finally, the reference committee evicts constant numbers from all committees and randomly assign them to other committees. The reference committee creates a reference block, and this reference block contains the random value revealed in the epoch I step, and the new list of all the members and what committee they were assigned to. So that is at the end of the epoch I-1 stage, the random value is generated in the epoch I stage, the solution is founded, and the reference block is gossiped the beginning of the epoch I plus 1 stage. In addition, these settings are handled in the reference committee. And then this is the node initialization and storage. So RapidChain is based on the votes of members, not the longest chain principle like Bitcoin. So therefore, when a new node enters the committee, the node does not need to download all the blockchain initially. So in other words, in order to verify the transaction that occurs later, only the set of UTXO is downloaded initially. At this time, the hash of the current UTXO set is recorded in every block to ensure the integrity of UTXO. So this is the conclusion. The first 1.3 resilient sharding-based blockchain protocol and RapidChain uses a distributed ledger design that partitions the blockchain across several committees along with several key improvements in significantly higher transaction throughput and lower latency.